Now, let's consider this single degree freedom simple example, which is a mass spring system. And let's derive the equation of motion for this system using all three approaches that we talked about. This is a single degree freedom system, so I expect a single equation of motion for this system. Now, if I consider first the Newtonian approach, first I will have to draw a free body diagram for the system, which is basically one single mass M and a spring force K times X, and there's the weight mg and the normal force N on the system. Now, I really don't care about the vertical forces because the motion is in the horizontal direction, in the x direction. So I will just take the sum of forces in x and set that equal to the m times acceleration. So sum of forces is m times a. The forces in x, we have only one force in the negative x direction, negative kx. That will be equal to m times the acceleration is basically the second derivative of the motion. The first derivative is velocity, the second derivative is acceleration. So I have x double dot for acceleration. And rearranging this equation with the variables all on one side, m x double dot plus kx equals 0, and this is the differential equation representing this simple mechanical system. We will call this equation of motion, the equation that if we solve we will end up with the motion of the rigid body as a function of time. So this is called the equation of motion. And we notice that it's a simple ordinary differential equation. So this is using the Newtonian approach, and as I said, it's a fast method, but you have to be careful because you're using vectors here, directions, signs, so any mistake in assuming the direction of the force or substituting signs in the equation, you will end up with the wrong equation of motion. On the other side, if I look at the energy approach, this is a conservative system. I don't have any friction or damping or air drag. I only have one force, which is the spring force. I don't have any external explicit forces in the direction of the motion. So this is a totally conservative system, and I can use the energy approach. For this system, the kinetic energy T is 1 over 2 mv squared, and the velocity in this case is the derivative of the motion, so that is x dot squared. The potential energy, we only have one source of potential energy, which is the spring, and the potential energy in a spring is 1 over 2 kx squared, and x is the deflection in the spring, which is equal to the motion of the mass. So now this makes the total energy of the system E, which is T plus V, is 1 over 2 mx dot squared plus 1 over 2 kx squared. Now this is constant, okay? So if I take the time derivative of this constant, I will end up with 0. So dE by dt is 0. And let's differentiate this energy terms. So the derivative of the first term, the 2 cancels the half, so mx dot, and then the derivative of x dot is x double dot plus 2, so I end up with k x, and the derivative of x is x dot because we are differentiating with respect to time. So we use the chain rule. The derivative of x squared with respect to x is 2x, but with respect to time, using chain rule, I would have to multiply by x dot when this is d by dt. So here's the final equation, and we notice that we have x dot common, so I can cancel x dot, and the final equation is mx double dot plus k x is 0, and this is also the same equation of motion that we got from the Newtonian approach. Now, it's a couple of more steps than the Newtonian approach, but there's a one advantage, it's a major advantage, is now we are dealing with energies which are scalars, scalar quantities. Scalar quantities do not have signs or directions, so that's very important here in this case. Even if I make a mistake in assuming the direction of the motion, it will not affect the final result here when deriving the equation of motion. I do not have any vectors, nor I have any signs. And the nice thing also is that everything is squared. So if you assume by mistake a variable to be negative, where it's positive, does not matter because you are squaring it anyway. So that makes this a more guaranteed method to get the correct equation of motion, but it has its limitations, which are basically conservative system, no external forces, no friction, and it's also limited to a single degree freedom systems. When dealing with multi-degree freedom systems, that are systems which have 2 or more degrees of freedom, this method will not apply. If we want to apply it, it becomes extremely complicated.